Right. So lower degree was denominator degree was higher, so there's a 0. And let's look at the other situations that we have. X approaches infinity. Or x squared minus x plus 1 over 2x squared plus 6. So if we have something like this, as x approaches infinity, the degrees match. So then what we do is we look at the coefficients.
And then the answer is 2.
And the rest of it still doesn't matter.
Yeah, so because the degrees match, let's look at the coefficients, so it would just be 4 over 2.
What if you have like 4x cubed minus x squared? It's just the biggest degree?
It gets so big.
Yeah, the rest of
It's
it.
so big.
But like, oh,
Because x cubed is increasing a lot faster.
wait, okay.
So here we have a situation where the degree in the numerator is larger than the denominator. So this guy is getting larger more quickly than this guy is, so this would have no limit. What's that? Yeah, it does like this. That's good.
Alright. And if you're trying to find the limit of x to anything else, you just plug the anything else in for x, right?
Yeah, yeah. So it's a good one. We'll do one of those.
And that's defined the
Discontinuity, right?
Let's say limit
But there
x
is,
approaches.
there might not be a discontinuity. If there is,
There's discontinuity if we can cross out the top and the bottom, if the top is faster, we've got the same action, right? Okay. Yeah,
That's
that's
what
what
it
was
was
as a whole. Oh, okay.
So let's review this. So let's say we have it. I may just give it to you in factored form, but I don't want to do that. I want to see how to do this.
When we first talked about it.
So So for here, if you were to find the limit as x approaches 3,
You would just plug in 3?
It's 0.
you gotta be careful, because what if we have a removable
So
discontinuity?
you have to factor it
In the sense that, like say graphically, for example, let's say you had something that was like this. Where let's say this is at,
So you have to factor it.
yeah, this is at x equals 3.
But there's not a discontinuity.
it'd be x plus 2, but x will equal 3.
Wait, it would be x plus.
For example, something like this.
Right, yeah.
This may not be the most accurate, but it's good enough in the sense that this graph here, if you think about the general idea is that I have something to the power of 2 in the numerator, I have something to the power of 1 in the denominator. If I just look at, okay, just the big picture here, a quadratic divided by a linear would give me another linear. So if this situation occurs, the limit as x approaches 3 would exist,
Right.
right? Even though we know there's definitely no value at 3,
But
right?
if you were writing the equation for the line, you would have to write x cubed equals 3.
Yeah. If you're writing the like.
You don't
the
necessarily
donation.
have
Though
to.
You're writing like the
Uh,
donating rate with red.
You know, you can be very specific and state that, but you can say y equals this, and it could look something like this, or there is a hole at 3. If there is a hole at 3, now how algebraically would we know this?
Wait, a question about this before you take it. So, okay, so you can still find the limit as x approaches 3 even though there's no 3 there. So why can't you just plug it in 3?
Well, if you plug in 3 as it's written right now, we're gonna have division by 0.
But it's 0
Okay.
over 0, so it just doesn't work.
There's
Um,
no
But it
hole
does,
at
you have
3.
it backwards.
So what we have to do when we see this is say, okay,
Oh, yeah.
is this removable? Is this removable? So we say, okay, this would be equal to, let's see if we can factor this guy. So let's say this is equal to the limit as x approaches 3 of, could we factor this?
Yeah.
No.
Yes, no, there we go.
Glad I know my question.
All right, so we see, because again, the limit is what value we're approaching. We can go ahead and we can basically consider this like a removable discontinuity. And so to find the limit as x approaches 3 of this guy, that's the same thing as finding the limit as x approaches 3 of just x plus 2.
Right, so it's 5, right?
Yeah, so this would be equal to 5.
And that means that that hole is at 5, right?
No, the whole would be at x equals 3.
Right, but 3, 5.
3, 5, yeah, would be like the coordinates of the hole if you go now.
Okay, so what if it wasn't movable?
Yeah, that's what I was gonna ask.
Okay. So if we had something that was non-removable, we would have a situation of there being, well, okay, as far as what you guys know with polynomial over polynomial, non-removable, you know, there would be an undefined limit or no limit,
Okay.
or division by 0. You couldn't remove it. And that'd be a situation where you have a vertical asymptote. Yeah, say for example.
So if you said it would be no.
No limit.
Okay.
Let's just say for example, let's say we had the limit as x approached 3 of, let's say, 2 over x minus 3. You practice. Very clearly you can see that there's no way to remove x minus 3. So this being said, there would definitely be a vertical asymptote. It really doesn't matter what the rest of the graph looks like, but you could definitely plot some points if you wanted. So let's say when x is 0, actually let me do some.
But when it's something like that, we just have to say no limit, like we don't have to say anything else. Because I know like pre-calc, we had to like, if there wasn't a limit, we had to say what the number was.
You know, if you had a problem that just says, this is like saying you have directions saying like evaluate the limit. Evaluate the limit.
You would just say.
We just say no limit.
Yeah.
Okay.
So then, One, two, three, that'll work. Doesn't have to be perfect for this particular purpose here. So at x equals 0, you'd have what, negative 2/3. No. When x is 1, you'd have negative 1. When x equals 2, you'd have negative 2. So you can kind of see what's going on here. When x is, say, negative, let's go negative 1.
negative on that.
Mm-hmm. Yeah, so do we see, is there a horizontal asymptote?
Yeah, it's here.
It would be 0, right? Because this is degree 0, this is degree 1. Again, the degree is higher, so this is getting way larger,
So
more
wait,
than this.
to find a horizontal asymptote, always you look at the degrees, and whichever one is higher.
Yes, to find the horizontal asymptote of a function, what you do is you are looking at in behavior. So you say let x approach plus or minus infinity and see what happens. And if when you have a fraction or ratio of two polynomials, yeah, it can be as easy as just looking at the degrees of each the numerator and the denominator.
So it's just gonna go like that, basically, and it's never gonna hit 0, it's gonna go right there.
Right, it'll get infinitely close to 0, but never actually get there.
It looks like that. That's crazy.
And then so let's graph some points to the right. So let's say when x is 4, and when x is 7, you have what? Yeah. So 7, you have 1/2. And you can see what's going on here. This would be good enough. You see, just get an idea of what it looks like.
Really good.
Thank you.
Much better than so let me do his job. So little bit.
Yeah.
Trying to get paid.
I feel like the blue is
There's something he's great he gets.
It's like I was thinking of
Okay,
it.
I'm rapper.
Does that mean there's an asymptote there? And they're like, no, like, stop this.
Yes.
If, are the same rules for the limit of x to infinity? Do they apply to the limit of x to negative infinity too? Same rules?
Yeah, good question. Yeah, and a lot of times you'll see as x approaches plus or minus infinity.
So, okay, cool.
Yeah. And the reason for that works out algebraically, like doesn't matter if it's 0 over -0, or -0 over 0, or 0 over 0. It's all 0.
Okay.
Good question. So here this would be no limiter. Does not exist. We find right. Does not exist. All right.
So wait,
Cool.
what, this is about infinity and negative infinity.
Yeah.
And so what are the limits for those things?
So let's say we go back to the original warm-up problem. It doesn't really matter if I write plus or minus, or just write minus or plus. So for example, let me put this in here. Plus or minus infinity. Same situation here. Yeah, it'd be the same scenario. So, like for example, okay, so negative infinity. So think about as you're getting really, really negative. So if we plug in, let's say, I don't know, negative 1,000. Okay. This would be a really large positive value, and this would also be a really large positive value.
So it doesn't matter.
Yeah, so it doesn't matter, 0 over 0 or -0 over 0, for example. But for this particular one, it's just going to be 4 over 2, regardless of whether you go plus or minus. Yeah, because they match, right?
Yeah.
Yeah, so if I can put -4 over -2, it's the same thing as 4 over 2. So the same was, for example, x to the third, and this was x to the third. This is the third power. It doesn't matter, -4 over -2, same principle as 4 over 2. So it doesn't matter. It doesn't matter if you're approaching y equals 0 from the top or from the bottom. We still say there's a horizontal asymptote at y equals 0.
So,
That's all it really tells you is how you're approaching it, the top or the bottom.
okay, so if it was 4x squared on top and 2x to the third on the bottom, and it was stood out here, it would be.
It would be 0.
Still be 0, but.
Yeah.
Okay.
Yeah. Okay. Does not exist. But if we took this, yes?
If you have a graph that, I'm going to understand how to state this question. Okay, so if you have a graph that has a vertical asymptote at whatever, and then it also looks like that with the curves, is there always going to be a horizontal asymptote at 0?
yeah.
Oh, cool. But there's always gonna be a horizontal aspect.
When you have a situation of a vertical,
Yes.
well, it's non-removable, so it's not necessarily true. Like, for example, if you have something that reduces to a parabola, yeah, I don't think it's necessarily true. And so, if we have the limit of the same guy as x approaches plus or minus infinity, 2 over x minus 3. Let's see that. Yes, bottom is a higher degree than the numeric. So we'll touch on limits there, continuity. It's pretty straightforward, I think. It's understood that if a function is differentiable at a point, then it's considered to be continuous at a point. Derivative of a function, Wolf's differentiation. You guys want to look at some chain rule problems, I think. Okay. So let's say, for example, we have, this is page 1. So say, for example, we have y equals the cosine of the square root of just the 3's under the square root x. And I'm not so concerned about you guys doing the substitution aspect of it, as long as you understand that you're working from like the outside and then you do necessary chain rule. So let's say we get a problem. So let's say we want to find y prime. So y prime. So this is where you look at the big picture. Okay, cosine of whatever. Okay, what is the derivative of cosine of x? Negative sine of x. Okay. Okay, so for this guy, we know that the general picture, the big picture, is negative sine, and then leave whatever is inside alone, and then times the derivative of the inside, which would be square root of 3. The derivative with respect to x of square root of 3x
No, you're right.
is the
It's
square root of 3. Just the coefficient with x.
Oh, yeah.
You can even do the power rule, 1 to the front, drop it down to 0,
So
x
I
to
was
0
just
to
thinking
1.
because I thought of the regular version, but I forgot that it was raised by x.
I think it's good if we just go through a lot of these. So then we'd say, okay, y prime, we just write it more properly, negative root 3 sine of root 3x. Okay. I'm just rearranging so it looks nicer.
Are we ever going to have to find a second derivative of the rest or something?
Yeah, eventually. So why not? Why not? Let's see if we can do it for this. It's good. But you mentioned it. Rebecca mentioned it. She did. No, it was her. No, that's good. It's a good thing. It's a good thing. Let's do that. It's good. Let's make sure we're clear here. So the question is, how did I get this last line? How did I get this?
By the front and you got it. Got it.
Okay.
Sorry. Stupid.
No.
So we're going to find y double prime. You would do you do the product?
Yeah. So yeah, exactly. So now let's go ahead and attempt y double prime.
But then, like, is the negative square root of 3 side one thing, or is it?
All right, let's see what we get here. So y double prime. I want you to view it like this. Like you have this guy times this guy. See, the big picture here is, okay, negative square root of 3 times the sine of something. Okay, so these are your two factors of your product. Okay? So product rule, and this is one of those, again, it's just, there's some things in calculus you just have to memorize. And this is one of them. For product rule, it is what you do, the derivative of the first factor times the second factor, plus the first factor times the derivative of the second factor. So the derivative of this is 0. So 0 times, leave this guy alone, plus leave the first factor alone, times the derivative of this guy. So the derivative of sine is cosine.
Wait, you have to do the chain rule.
So we have to do the chain rule. So chain rule is built into this. Sorry if I'm saying in your way, guys. I'll get out of the way in just a second. Times the cosine of square root 3x times the derivative of music is this chain rule, which is square root 3.
Okay, so 0.
Let's make sure we understand this before we move on.
0.
I'll just repeat. So derivative of this guy was 0 times leave this guy alone, plus leave this guy alone, derivative of the second factor, which is this. Just make sure you're able to have little compartments in your head. Like, okay, I'm doing this, and then now I'm doing this, and the derivative of this is this. So just try to make sure take your time, get it correct piece by piece. Okay. So then, of course, this goes away to nothing. So we would have y double prime would be equal to 0 plus, if you simplify this, it's like negative root 3 times square root 3 is negative 3. So plus negative 3 times the cosine of the square root of 3x. So y prime would be equal to negative 3, sorry, double prime, negative 3 cosine of square root of 3x. That's y double prime. And y prime, we have that. Now these are not too bad. As you know, if I had to take the third derivative, it wouldn't be that bad. It would be similar to this. There's others that can get incredibly worse. You just gotta be careful.
Because the second is really smaller, which means less times 1 was. My short must have been when all this stuff was general and crap.
All right. So there's one that's 5 is a little tough. We'll go through 5 though. Yeah. You okay? Okay. Why isn't this one? Let's get this done. We're out of time. Sure. Actually, I'm gonna move on. You can go right down to paper. It's page 153, number 7 through 11.
7, 9, and 8.
Yep. All right, page 153, number 7 through 11 odd, and I'm about to go back to the next problem. Didn't take that one right down the paper. All right, so this one, hopefully you won't do any nastier than this, probably not. So, we have this, so let's get started on this.
I don't understand how this is gonna work.
Oh, we'll see how this works.
So I,
What question?
this is so hard, I have to memorize all of these.
Yep.
So you would use like the.
Okay.
Yeah.
So the first thing is that furthest on the outside is we have this 2. This whole thing is being raised to 2. Okay. So think about
Isn't it 1 plus cosine?
think
x?
about
So sine x
Yeah,
minus
y
sine
times
squared
so
times
to
sine
start off
x
here,
squared.
we'd say y prime 2 to the front. Leave this inside alone.
But then you do the closer one.
Then this drops down the power to 1 times the derivative of the inside, which is a quotient. So I could for right now times the derivative of respect to x of this sine of x over 1 plus sine of x.
Oh, okay.
Yeah, so the big thing with this chain rule is outside in, so 2 to the front, drop it down, then the derivative of the inside. So then just focus on that, okay? The derivative of the inside, oh, okay, this is going to end up being quotient rule. Okay?
The bottom right
So-
and the top, which is cosine, right? So sine x.
And this gets out at 11:15.
We got 4 minutes.
So go
It's
for it.
11:11, make a wish.
See if you guys can finish.
I basically